Okay, I will go. So, hey everyone, welcome to this talk. The name of the talk is polymorphism. This is not even my final form. My aim during this talk is to give you the insights behind polymorphism and just show you some various forms of polymorphism. And most of these forms are available in Scala. So my name is Stéphane Tankoua. I'm working I live in Paris, in France, and I work there for a company whose name is Singularity. This is my GitHub and my Twitter. So the name of this talk is a reference to a sentence this character said. The name of this character is Frieza, and just like polymorphism, he has various forms. So I'll start with the genesis, and you see I will start very easily. I have a lot to say, so I hope I will say all that. So we started with the definition of polymorphism. So a language is said to be polymorphic if variables can have more than one type. Polymorphic functions are functions whose operand can have more than one type. On the contrary, in monomorphic languages, variables can have only one type. So now I will give some historical element about polymorphism. Polymorphism was introduced by Christopher Strachey in this paper, Fundamental Concepts in Programming Languages. He defined two forms of polymorphism, parametric and ad hoc polymorphism. Then in 1985, Cardelli and Wagner redefined the strategic classification of polymorphism by adding more forms. And this paper is very interesting. I recommend you to read it. And my talk is inspired by this paper. So these are the four forms of polymorphism defined by Strachey and Cardelli in their paper. So you have parametric polymorphism, inclusion polymorphism, overloading, and correlation. So these four kinds of polymorphism are classified into two groups: universal polymorphism and with universal types of polymorphism. The idea is that when we define a function, the behavior of that function will be uniform for all the input types. Whereas with ad hoc polymorphism, the behavior of that function will depend on the input type. So universal polymorphism is true polymorphism, whereas with ad hoc polymorphism is just a syntactic sugar for developer. So I will start. Before seeing the various kind of polymorphism, I will give some element of syntax, because the example I will show will be in Scala, TypeScript, or Haskell. So I'll just give you the syntax of Scala. On the first line, I define a value. This is how to define a value, and this is the type of my value. My value is immutable. That's why I'm using this keyword. Right here, I'm defining a tuple. Then I define a function. The input type of that function is here, and this is the output type. And right there on the last three lines, I define an alternative. So that this is an alternative between two records, and this is a record. It's just a class with a label, a field which has a name and a type. So that's it. This is the syntax of the element I will use in Haskell. In Haskell, you just have to remember that first we give the signature of our value or a function, then we give the implementation. So for my value, I first give the type, the signature with the type of that value, then I give the implementation. The same goes for tuple, and the syntax of a tuple is very close to syntax of a tuple in Scala. This is a function. Here, I give the signature of that function. The input type is an integer, and the return type is a string. And if you see in Haskell, all parameters are clarified. It means that if you see a function from int to string to int, that function will take two parameters, the first one being an integer and the second one being a string. On the last line, this is a record in Haskell. This is an alternative in Haskell, and that alternative can be construct with either the record, this record, this constructor for this record 1, or the constructor for record 2. And this is the syntax of TypeScript. This is how we define a value in TypeScript. This is how to define a function in TypeScript. This is another way to define a function as a lambda function. And this is an alternative of two records, record 1 and record 2. And the records are written with the syntax with a syntax close to the JSON. So that's it. Now we see the kind of polymorphism. The first kind of polymorphism is parametric polymorphism. In OOP language, they are used to parametric polymorphism, and this is also called generics. So with Scala, if you see an example, where I define a function from a type A to a type, define a function length with a type parameter, between brackets. That function takes a list, and that function will return an integer, which is the length or the size of that list. So that function, when I will implement it, the function should be, the implementation is agnostic to the type parameter A. So that function will work for any A. And when I will call that function, I have to specify the type parameter, to specify the value of the type parameter. So when I will call the length function, I specify the int. I specify the type parameter to be an integer. Then the compiler will infer that function will receive a parameter of type list of int. And this is the same with Haskell, but in Haskell, you just have to remember that any type parameter in the signature, any parameter which is unknown to the compiler is a type parameter. So A is a type parameter since the compiler doesn't know it. And the same goes for TypeScript, where we define the type parameter with the lower sign and upper sign. So now we'll talk about inclusion polymorphism. So what inclusion means. So the type A is included in or is a subtype of another type B when all values of type A are also values of type B. That means exactly when A, considered as a set of values, is a subset of B. I will illustrate that with an example. This example is in Scala, and in Scala and in many OOP languages, inclusion is achieved with subtyping and inheritance. So in Scala, to have inclusion, what we just have to do is define a class, like here, person, with 2 attributes. Then we define a subclass of person. So that class employee extends person. And so that class has the same attributes than person with an extra attribute, which is manager type Boolean. And if I have an employee, I can put that employee into a variable expecting a person. So this is inclusion. And there is a little difference between what inclusion is achieved in Scala and in TypeScript. I will show you the difference with an example. In Scala, for example, if I define 2 classes, A and B, with exactly the same attributes in the same types, I have 2 values, one value of type A and one value of type B, instantiated with exactly the same values. And if I try to compare that 2 values, I will get the result will be false. Whereas in TypeScript, where if I have 2 types with exactly the same attributes in the same types, I have 2 values A and B, one of type A and the other of type B. If I try to compare those values, I will get true, because in TypeScript the equivalence is structural. equivalence between two types is only based on the structure of that type. Whereas in Scala, in order two class will be equivalent only and only if they have the same structure, so the same attributes with the same type, and they have the same name. And there is also a difference between structural and nominal type with subtype if you consider subtyping. So I will show that with an example. If you have a class A, you have a class B which extends A with an extra field. You have a class C with exactly the same fields as B. If you have a value of type B, we can put that value into a variable expecting an A. Whereas if you have a value of type C, that value could not be assigned to a variable expecting an A, because here we have to explicitly say that class C extend class A. Whereas in TypeScript, if you have two types, A and B having an extra parameter, if I have a value of type B, I can put that value into a variable expecting an A, because with structural type, the subtyping relation is implicit, whereas with nominal types, as in Scala, the subtyping relation is explicit. I have to explicitly say that, like, this class extends from this class. So that's the difference between the two. Now we talk about coercion. Coercion polymorphism is something we used to. Coercion is just a semantic conversion from one type to another type, which is a type expected by a function or a variable, for example. And this is something we have in TypeScript with falsy values. So with falsy values, if I have an object of type A, for example, if the bank parameter just before that object, I will coerce that object to a Boolean. So this is coercion. This is coercion done at runtime and automatically by the language. Whereas with that on that object, if I call the method, the function to string, the method to string on it, I will get a string. This is also a coercion from the object from type A to type string. But this is done by hand. This is me. This is the here the developer explicitly write the call to string method. So the last form of polymorphism defined by Strache in this paper is overloading. And overloading, you have overloading in OOP language, like in Scala. In this example, in Scala, I have a class printer, and printer has two methods named print state. The first method expects its parameter to be a string. The second method takes a parameter of type int. And if you have an object of type, if you have a printer and we call print state on it with a string, you will call the first version of that method. So we call that one. So overloading is just, the idea behind overloading is just to have many functions which has the same name, and we call the right version of these functions depending on the context. Right here is the parameter. So now we see some intermediate features of polymorphism. And the first features I want to talk about is type classes. So type classes were introduced in 1988 by Philip Wilder and Stephen Blatt, who are working on the Haskell language at that time, into that paper, which is an interesting paper. So type classes were initially implemented in Haskell. And why Haskell? Because they are willing to do at this time is to have polymorphism, especially ad hoc polymorphism, especially overloading, because at this time Haskell doesn't support subtyping. It still does not support subtyping, but they want to implement operators like plus or multiply on the numeric types, and they also want to implement operators like the functions like toString, or to implement equality between types. between the values of the types. So type class was meant to achieve that. So this is an example. I will show you as an example the type class for equality to check if two values of the same types are equals. So that type class is defined with like this, like with the syntax class a, where equal this equal is a method of a type class, and this is the type of that method. So that method is a function which takes another a and returns a boolean, which is true if the two values are equals. And we could read it as type A belongs to class X if there is a method equal defined on it with the right type. And we could create instance of that type class for a type. So here we create instance of X for a type int, and we give the right implementation, the underlying implementation for the equal method for integers, which is Xint. And with that instance, this is a way to prove that type int belongs to the class X. And if you want to define a function which will use that constraints, you just have to specify it like this with a fat arrow, and then we give the signature of that function. So that function will take a list of a, we take an a, and return a boolean. So with that function, you will see that we need our type parameter a to be an instant to belongs to class X. And if we call member with a list of integer and 1, for example, we get a value which is true for us. Yeah. And if we call it with a list of boolean and a boolean, we get a compile error because the compiler will check if there is an instance of X for a type bool into the program. And we didn't define an instance of X of bool, so we'll get a compile error here. And with type class, we can have composition. Composition is very simple. In our example, if I have a type A which belongs to class X, I have a type B which belongs to class X, I could define an instance for the type tuple AB. So that's it, that's composition. And with type classes, we also have subtyping. And what subtyping means, I will show that with an example. Here in that example, we define the type class ord, and that type class will allow us to compare values of a same type. So with the two methods, lower than or lower or equals than. And that type class, in order to the type A to belongs to the class ord, that type A should first belongs to the class X. That's why we specify that constraints here. And then we could define an instance of ord for integer, for example, then define functions with that constraints, and then use it. So now I want to talk about how type classes are implemented, and it turns out that in Haskell, type classes are disregarded in a very simple way, in very plain old Haskell. And to implement type classes, the first thing we should have is dictionary. Dictionary is just a record whose attributes are just functions, which are the implementation of the method of that type class. So right here we define a dictionary xd of a. That dictionary is just a class, and this is the constructor of that, a record. This is the constructor of that record, and the implementation is just the function, which is the method equal for class X. Then we define the values. Right here, we define the value for int of that record. And when for the functions which use the constraints ek, that function are just rewritten as regular functions with an extra parameter, which is the first one. And that extra parameter is just an instance of that type class for the type A. So that constraint is just here, just an extra parameter, which is passed implicitly. So right here with type class, you have an implicit parameter passing mechanism. So that's it. That's it to implement a type class. And with subclassing, the only difference will be that for our subclass, we'll define a record. Our record will just take as a first parameter the instance for the superclass for our type. So right here we take as a first parameter an instance of xd of a, and then we could, and then for the rest is just the same. So the implementation of type class in Scala is just straightforward, because the first thing we need is parametric polymorphism, because we need to have a type parameter with type classes. Type classes use parametric polymorphism, so you need to have parametric polymorphism. For the record type, we just use a tray as an interface for that type. We define values as implicit values, and we give you the right implementation for the type. Yeah, you give the right implementation for type int, and then we define our function that will take as implicit parameter an instance of that type class for our type A here. So the implementation is very straightforward in Scala, if you take the disregard version of type class in Haskell. And for subtype class, it's very simple. We just have to define a trait which extends from another type class. It's very simple. And with type classes is what you have seen just before is overusing. And with type class, we can also have coercion. And to have coercion is very simple. You just have to define a type class coerce with two type parameters and a function in the method coerce, which is a function from type A to type B. And then I will just give in the instance, I just give the implementation of that method. So that's it. Now there's another interesting thing with parametric polymorphism, and this is that version of polymorphism is polymorphic values. And polymorphic values are very simple. I will show that with an example. If I have a function id from A to A, and that function I will implement it as with a lambda function. So that function id is just a value right there. It's a lambda function, so it's a value, right? That function could be also written like this, with an explicit for all. And that function, I could assign that value to a variable expecting an int to int, a function from int to int. I could also assign it to a variable expecting a function from double to double, right? So that ID value belongs to the type int from int to int, and also belongs to the type double to double. So this is a polymorphic values, and it turns out that the type of ID is for all A to A. That type it's a type parameter, and yes, this is a type. So this is a polymorphic value. And it turns in TypeScript, we have polymorphic values. You just have to define its. You just have to define the type of your function with a type parameter like this. And in Scala 2, we don't have polymorphic values. It's very simple to show you that. We could define ID here, and if that ID could be assigned to a function into int, but that ID we could not define ID as a value. And if you try to see the type of ID, you see the type nothing to nothing. So, but polymorphic values are coming in Scala 3. So this is interesting. Then the last form of polymorphism, another form of polymorphism, which is interesting with polymorphic values, is higher order polymorphism. Higher order polymorphism is very simple. I will show you an example. So if you define a function twice, which takes a function from A to A for all A, that function also takes a B and returns a B. And the implementation will be very, very, very easy. That function I could call the function twice with ID and 3. I will get 3. That function is said to be rank 2 polymorphic, and ID, the function ID, is rank 1 polymorphic. The n rank is just how nested is that polymorphic value I take as a function is into one level of parentheses. So it's rank 2. That rank 3 is rank 3 polymorphic because that polymorphic values is in 2 levels of parentheses. So that's it. And with higher order polymorphism, there is something you should be aware of. If you define, for example, a function sec like this, which adds 1 to its input parameter, we define another version of twice without a polymorphic values. With the same implementation, I can call that version of twice 2 with ID and 3. It works. I can call it with twice with suck and 3. It also works, but I could not call it with suck and 3 because twice expects its parameter to be a polymorphic value, or suck is a monomorphic value. It's a monomorphic function. So that's it. The last thing I want to talk about is existential type. I don't have many time left, so I'll try to talk about it quickly. Existential type are just another with parametric polymorphism. When we write something like this, we just want to say that for all type A, the expression P has type T of A. With existential type, which is another way to quantify on a type, when you write something like this, what you want to say is that for some type A, P has type T of A. What's the difference between the two? With universal quantification, when we implement the function, the type A is unknown to us. So our behavior we have to write the code once for all types. Whereas with existential quantification, when I will implement it, the type is known. I will set the type. Whereas when the difference, there is also a difference for the person which we will use the value of that type. With universal quantification, the person which will use the expression of that type has to set the type. For the length function, for example, I set the type to int when calling the length function. With existential quantification, I didn't have to set the type because I don't know all I know is that there is a type, there is another underlying type. So that's it. I want to ordinary values could be seen as belonging to existentially quantified types. Like the tuple 3, 4, for example, could belongs to A being int, and that tuple could also belong to for some A being that tuple, right? And the upper and the lower bound could be written with as quantified types. And for the type any, it could be written like this. For some A, I have an A, because when I have a value of type any, I know that on the underlying type of that value, there's another underlying type for that value, but I don't know the type. So that type is unknown to me. And for nothing, we could just write it as for all type A, I can give you a value of that type. And if you actually try to write a value of type int, string, function, int, string, this is not possible. So that's why the nothing type is inhabited. And if you take, for example, the tuple with 3 and length, it could not belong, for example, to that type for some A, the tuple A and the function A to int, because even if we take A to any, because the length function expects its parameter to be a list of something. And a type any is wider than a list. So this is not okay. So the thing I want you to remember is that with existential types, the purpose is to hide the type inside a type. With that existential type, for example, the type A is unknown, will be unknown outside. So when I will define a value of that type, I will set a value for the type A, but it will be unknown outside. And if I rewrite this type, if I like a record, like this, for example, you will see that this looks like a regular object, but with a value, a function which operates on that value, but I don't know the type of that value, the value inside my object. So right here, I'm hiding a type inside a type. So this is second order information hiding. And this is how to create an existential value in Haskell. Is just with the for keyword, but my type here doesn't have a type parameter, so the type parameter is hidden into the constructor. And with Scala, the first way to create an existential value, yes, the existential type, is with that underscore, because when I will create my list here, I will hide the type of the element of my list. So that's it. And there's two other ways to create an existential value in Scala. The first one is to define an abstract type. So right here in my tray, I define an abstract type A, which I will use then. And when I will create an instance of that tray, right here, I will set a value to A, the type to A, but outside that type will be unknown. And if we try, we get a compile error. And there's another way is to define a tray, that an implementation with a type parameter. When I will have an instance of x2, I won't be able to know which is the type I've set to the subclass. So that's it. And this is an example I will show you very quickly. In that example, just want to implement a stack which will work for any input type. So that stack will store integers or string or vehicles, I don't know, any types. But the inner representation of my stack should be hidden. So my stack, the type of the structure I will use to implement my stack should be unknown to the person, which we will use my stack. So right here to implement, I define my stack as a tray with a type parameter here, item, and an abstract type, which is the type of the structure I will use to store the element. And if I create values of my stack, I will take a type parameter and I will set the internal structure to be a list of integers. So I will store my item into a list of items. Or if the type of item is integer, it will be a list of integer. I could have another version of that stack to store it as a map and an index. And if I define a function to operate on that stack, that function, for example, could create a stack, put a value into it, get a value from it without knowing what's the underlying, the the structure I use inside that stack to store my values. So that is for me.
It's about higher rank polymorphism.
Mm-hmm.
You said that it wasn't supported in Scala at the moment, but would be probably in Scala 3.
Polymorphic values? Polymorphic values.
Polymorphic values, yes.
Yes.
But as far as I can tell, it's still not supported because I tried your example and it still returns nothing. Nothing. So when do you think it would be implemented if it
Okay.
would be?
Okay. What I really mean when I say that it's actually not supported is that in Scala there are workarounds to have polymorphic values, and one of the workarounds is something I showed on the last example, if you remember, or if the on the last example with existential type, when I created the generic stack, I created another tray with apply method, and that apply method will give me an instance of the generic stack, of the generic stack, and with that trick, with a tray and an apply method, I could get an instance of the monomorphic type. So this is what I really mean when I say that polymorphic values are not supported. I was meaning that I can have a value. I can actually define a value which has a polymorphic type. So that's it. And actually, this is a workaround, and some libraries like Pascal, I think so, Pascal in Scala, give some stuff like that to have polymorphic values. But
what library? Sorry.
Pascal, I will give you the link. Pascal, I will try to find it on GitHub and share and give you the link. But all the library have will just help you to define a tray and then give you multiple instances which are monomorphic. So, but polymorphic values, real polymorphic values, will be available in Scala 3, and I don't know when it will be, when Scala 3 will be out. Maybe at the end of this year we'll have some early release, so we could just we'll be able to play with it.
But do you have a link where they commit to make this available, or is it just an impression?
No. I will share the link, but I saw a blog post on the DOTI of the blog post of the DOTI team who are talking about that.
Okay, I'll look for it.
I will share it.
Okay.
And interesting, are you trying to use Scala.js?
No.
No.
No. Like I just said before, I've done some front-end development, but most of the time I'm just a back-end developer, so I'm just working with server-side libraries.
Okay, thanks. What Scala should adopt from other languages?
There are very many things I could say. The the features. Right now, there is one features that I really want is that features which is bring by SCP-35 opaque types. Right now, I really want opaque types because in all my on all my projects, we just used to define case classes which extends from any val, and that case classes will only contains a string or an integers, and that case classes will just help us to model some business data like ID, for example. And I think that opaque type is the features which will help me a lot in my day-to-day work. So this is the thing I really miss right now.
Okay, indeed, it was a phantom types in old version of Scala. Yes, but now they broken. Okay, thanks.
And there's a way with phantom type. Phantom type, in my opinion, is very phantom type is using phantom type is interesting, but it's not very beginner friendly in my opinion. And if, for example, there are libraries which propose opaque types, for example, but it's not beginner friendly, and it's not beginner friendly enough to add it on the project and to convince other people, because with functional programming on my part of my day-to-day job is just to convince other people to use some stuff which will help us when we are writing code. So with all the library I've tried for until now, it's not easier for me to write an opaque type.
Okay.
What could I say as a final word? Maybe I will just say thank you, because it's my first time as a speaker or attendee in the ScalaUA conference, and it was I really liked that conference. It's very interesting. So thank you for that, and thank you to the attendee and those who have seen this talk. Thank you very much.